Number 18, identical net forces. Aren't they cute? Act for the same length of time on two different spherical masses. Which of the following describes the change in linear momentum? A momentum problem of the smaller mass compared to the larger mass. A momentum problem, a momentum equation. J equals integral f dt equals change in momentum. Let's simplify that maybe a little bit. I feel okay simplifying it because the forces, they're the same, times, they're the same. We've got one mass is smaller, and that means delta P is the same. That means delta P is the same. See, a couple of people answered B, but B is not correct. C is correct. The change in momentum is the same. It's true that the smaller mass thing travels at a bigger velocity, and the bigger velocity thing goes at a smaller. But that's not what they're asking. That's not what they're asking. But I don't like this question because they mention spheres, and then they're talking about linear motion. They're being tricky. A block of mass 2 kilograms initially at rest is pulled along a frictionless horizontal surface with the force shown as a function of time. Question 6. The speed of the block at t equals 3 seconds, and we have here a changing force. A changing force makes the kinematic equations hard to use. A changing acceleration, but we have impulse is equal to change in momentum. When you see the force time graph, you should think to yourself, impulse is equal to the area under that graph, a triangle. 1/2 base times height, that's the impulse, is equal to the change in momentum. We started at rest, we have a base, we have a height, we have a mass of 2 kilograms. The velocity is 6.75 meters per second. A lot of people said B, 4.5 meters per second. I don't know how you got that. I bet I can figure out. I couldn't figure out how you got that. So if you got B, let me know how you got B, but the answer is C. A stick of mass m and length L has its mass distributed non-uniformly so that its center of mass is 1/4 L from the left. I wonder if people just gave up at this point on mass. M is attached to the left side of the stick. What mass, big M, must be attached to the right end of the stick so that the system will not rotate if it is pivoted about its geometrical center? Goodness, torque is equal to RF perpendicular, and we have torque. The counterclockwise torques balance the clockwise torques here, so we have m times L over 2, that's from the mass on the left, times m L over 4, that's the center of mass of the object. The mass of the object itself is equal to capital M L over 2, and do the math.
The elliptical orbit of a comet is shown above. Positions 1 and 2 are respectively the farthest, call it the aphelion, and the nearest, the perihelion, the nearest position to the Sun. At position 1, the distance from the comet to the Sun is 10 times that at position 2. What is the ratio of v1 to v2 of the speed of the comet at position 1 to the speed at position 2? Well, you might think about using this equation here for velocity. Fight that temptation. That equation is no good for velocity in this case. I've made this mistake before, but why is it no good? That equation only works for a circular orbit, and you do not have a circular orbit here. So what do you have? And I know what you're thinking, we have momentum. What does this have to do with momentum? Well, just as a net force can change the momentum of a system, so too can a net torque change the angular momentum of the system. This is an invitation to the rotation unit. There's a lot of rotation questions, so I want to sneak this into the momentum unit. We're talking here about angular momentum. There's no net torque on the system. That Sun provides a central pointing or a towards the Sun pointing net force. Gravity's a net force, but it's not a net torque, meaning that L, your angular momentum, stays the same. That's a cross product. More on this on the rotations unit, but the angular momentum, mvr, is conserved throughout the entire orbit. That means that when your r is small, your velocity is bigger, and when r is bigger, your velocity is smaller. You might recognize this as Kepler's second law. And looking at the equation, 1 to 10, that's the ratio of the speed at position 1 to the speed at position 2.